So, thank you again. I'll repeat that it is a great honor to give these lectures. So, basically, as it says on the slide here, so what I'm talking about representation theory and geometry. Last lecture was mostly about representation theory. This lecture will be more about geometry. And I just want to recall some... and also, here you have the slides of these lectures all as one file. And also this is something like a doubled version of the talk that I gave in Rio. Okay, so let us recall some things from last lecture. I explained this theorem. So this is very, very important because it's some kind of guiding principle for everything that we're doing. That a representation theory of a finite group over G, over the real numbers or over C is semi-simple. And I explained the proof, which I won't go over again, but I just recall these two basic points, is that you somehow prove this theorem by introducing extra structure, namely this positive definite geometric structure. So if I have a real representation and it has a symmetric invariant form, then I can split it, then given any sub-representation I can split off a complement. And so somehow you introduce extra structure in order to show that something is semi-simple. It's a very important principle. And also I explained this kind of extraordinary fact that on a complex representation, if it's an irreducible representation, there is a unique geometric structure up to scalar. And so it's kind of remarkable. So imagine that I give you a vector space. Then on this vector space, there's many different notions of geometry. There's many different notions of, for example, when two vectors are perpendicular. But what this is saying is that if this vector space is equipped with irreducible symmetry under some group, then in fact there's a unique geometry up to scalar. Okay? It's one of these things that is often in mathematics that's both trivial and also very surprising at the same time. So what we also discussed is Weil's theorem, the semi-simplicity of representations of compact Lie groups. We discussed the Kazhdan-Lusztig conjecture. So we have these Verma modules which are infinite dimensional representations. And then I described how their structure, the simple representations that occur inside them, are rather complicated, but that they're given by Kazhdan-Lusztig polynomials. And these Kazhdan-Lusztig polynomials are certain inductively defined polynomials. And I also explained the Janssen conjecture. So I just want to recall from the last lecture that we imagine some module as being something like a molecule. So this was our Verma module, delta lambda. So these are some kind of atoms in my molecule, and then I want to know the structure of this molecule. And what the Janssen conjecture is saying is that this module has a filtration such that so once you take the associated gradient of this filtration, then everything is semi-simple. It's quite a remarkable thing. This is what the Janssen conjecture was telling us. And in these situations, in Weil's theorem and in the Janssen conjecture, somehow geometric structures were playing an extremely important role. Okay? So my apologies, if you weren't in the last lecture, it won't be so important, but it's rather important for this slide. Okay, so now I'll explain a bridge to geometry, and invariant forms will again be extremely important. And we'll see these two themes again. So you show semi-simplicity via introduction of geometric structure, and this geometric structure is essentially unique. Okay? So now we can change gears entirely, and I want to discuss the flag variety. So SLNC denotes the special linear group of n by n matrices, complex matrices of determinant 1. So a Lie group, also an algebraic group. And we consider this flag variety, which initially just seems like a kind of random thing to do. So we consider full flags on Cn, so a nested chain of sequences, this is called a flag, of subspaces which of increasing dimension, so dimension 1, 2, 3, up to n. And the set of all of these flags has the structure of an algebraic variety. So if, for example, I just fixed one of these VI's, so I consider a subspace inside Cn of dimension I, then this is a Grassmannian, which classically has an algebraic structure. And then you can think about this as sitting inside a product. So each of these guys is parameterized by a point in the Grassmannian. And then these inclusions are some kind of algebraic condition on my subspaces. And so I get that this flag variety is in fact embedded inside a product of Grassmannians. So it's a complex algebraic variety. So this flag variety is a smooth projective variety. So it's projective because it's a closed subset inside, a closed subvariety inside a product of Grassmannians, and these Grassmannians are in turn projective. It has a transitive SLN action. So given two bases of a vector space, I can move one to another by an element of SLN up to perhaps I need a scalar. And so these, if I have two flags, I can refine these flags to a basis such that this is taking the first basis vector, the second one, etc. And then there'll be a unique, there'll be an element of SLN that takes my one flag into the next one. So this is has a transitive SLN action. And kind of the reason that the flag variety is so important is that it's the unique largest such variety. Okay? So if I want to study SLNC, this acts on many different varieties. But if I want my variety to be projective, then in fact, and I want the action to be transitive, so I want a homogeneous space, then in fact this is the unique largest such variety. And it's a very common theme in geometric representation theory to relate something about SLNC to something about this flag variety. Okay. And just a simple example to keep in mind, flag 2, so this is the set of subspaces of dimension 1 inside C2, which is the same thing as lines in C2, which is the same thing as the projective line over the complex numbers. This is the flag variety. So often in representation theory and also in number theory, when you have objects like this, so you might be studying this flag variety, and you realize that it's an important object, but you would like to describe it in terms of group theory. So you would like to describe it purely in terms of SLN, and that's what we'll do now. So this is a nice description to begin studying this object, but when you want to go further, it's nice to have some group theory. So we consider this coordinate flag. This is the kind of first flag that you would write down. And if we consider its stabilizer, so it should map this vector to itself, this line to itself, so that's this one here. It should map this subspace to itself, which gives us these two twos here. And so we get that it's the stabilizer of this coordinate flag is precisely this upper triangular matrices in SLNC. Okay. And so we get this group theoretic description of the flag variety. It's SLNC modulo B. This is a description of a homogeneous space. And this description is very useful. One of the reasons is that this B is what's called a Borel subgroup, and so now this makes sense for any reductive group, the notion of a flag variety. So we can make sense of a flag variety for any reductive group, like symplectic group or E8 or something. They all have a flag variety. A very important fact about the flag variety is that this Borel subgroup has finitely many orbits on the flag variety. So in our simple example of n equals 2, so if we think about our point at infinity, so here we have P1 of C. So this is a big Riemann sphere. And then if we declare that infinity is this line E1, then the upper triangular matrices act transitively on this piece and fix this guy. And so we get a decomposition into two pieces, one point and the rest. Yep. So these are the B orbits. And in this particular case, so these orbits are classified by the Weil group. So in this particular case, the Weil group is S2, the symmetric group S2, and it has precisely two elements, namely identity and the thing that swaps 1 and 2, and these are the two orbits corresponding. So again, this is kind of where this group theory is useful. So if you think what we're doing in SLN is we have some matrix, and what we're doing is multiplying on the left and the right by elements of the Borel. So here we have an arbitrary matrix, and we're asking how can we simplify this matrix by multiplying on the left and the right by upper triangular matrices, which is the same thing as saying, what can I do when I'm allowed to do row and column operations, but only in one direction? Yeah. And so what you can do, for example, if you have a 1 here, is you can make all of these zeros. And when you keep doing this, what you get left is a permutation matrix, which is precisely an element of the symmetric group. Yeah. So this is Gaussian elimination, essentially, this Brouillard decomposition. Okay. So now Schubert varieties. So what we can do is we can take one of these orbits. So this is an orbit of a Borel subgroup, so it's a rather simple thing, and we can close it up. And it turns out, it's not initially particularly obvious, but when you do this, kind of all hell breaks loose. So these are rather complicated spaces. Okay. So these are so-called Schubert varieties. So in this example, this point is already closed, and so when I close it up, I get itself. And so this is an example of a Schubert variety. Whereas if I take the open bit and close it up, of course I get P1 of C. So these are my two Schubert varieties in this case. But don't be fooled by this example. The Schubert varieties are usually singular, and they're very, very complicated things to understand geometrically. So Chevalier, who's one of the kind of greatest mathematicians of our field in the 20th century, he actually believed that Schubert varieties were smooth, always, for some time. And so you can be forgiven for thinking they might be smooth, but they are not. Okay. So remember this Kazhdan-Lusztig conjecture. So this is saying we have this Verma module, and its structure in terms of simple modules is given by the value at 1 of some Kazhdan-Lusztig polynomial. Now this is something that lives in the world of representation theory. This is the structure of Verma modules. And then we have this remarkable theorem of Kazhdan-Lusztig that they proved just after stating their conjecture. So I'll try to give you an idea of what this means, but I'm not explaining everything. So this is a polynomial in Q, and it has it's defined by some inductive algorithm, but that only depends on the Weil group. And on the right, what you have is, so this is a Schubert variety, and what we are doing is taking some cohomology groups of this Schubert variety at a particular point, some kind of local cohomology groups, and then taking, this is basically a Betti number. So this is a graded vector space, and we're taking its graded dimension, essentially. Okay. So this is the local intersection cohomology of a Schubert variety. So on the next slide, I'll come back to this in a second. So this is an example of what's going on. So here is a singular quadric inside C4. The set of points that satisfy this equation inside C4 look something like this. So this is a real picture, but you have to imagine that it's not too bad a picture of what's going on. And these sheets of even though they look like they're real dimension 2, these are actually complex dimension 3. So this is complex 4-dimensional, and then I'm imposing one equation, and so this is actually complex 3-dimensional. And this picture is roughly accurate. So every point is smooth except for this one singular point here. Okay. And so what is this? So local intersection cohomology is some very subtle topological invariant of the singularity. So if we take it at a smooth point, it just spits out Q in degree 0. So if we take the local intersection cohomology here, then we just get Q and then 0 elsewhere. But in this particular example, if we take the local intersection cohomology at 0, then we get interesting intersection cohomology groups, namely Q, 0, Q. And in the language of Kazhdan-Lusztig polynomials, this would give us a 1, and this is giving us a 1 plus Q. Okay, so I'm measuring. So part of the theorem on the previous slide is that these odd values are always 0. And then I measure the even ones, take the dimension to get the even ones. Okay. So this is actually a real life example. So this singularity happens in a Schubert variety in SL4. And this is exactly the one example that led to the Kazhdan-Lusztig conjecture. So this is the first singularity of a Schubert variety. So I'll just go back and explain this again. Okay. So this is a Schubert variety. This is a point of the Schubert variety. This is a graded vector space. I essentially take its Poincare polynomial to get a polynomial, and the statement is that this polynomial, that in principle is very difficult to compute, is actually given by a rather simple inductive algorithm. And before we saw that all the Schubert varieties in for n equals 2, namely we have two Schubert varieties, namely this and a point, so these are both smooth, and so this says all the Kazhdan-Lusztig polynomials are 1, and that's what we saw in the last lecture, that for SL2 all the multiplicities are 0 or 1. So now I go into kind of speedy version. So I don't want to explain too many details about this, but this is the extraordinary proof of Bailinson-Bounstein and Brzezinski-Kashiwara of the Kazhdan-Lusztig conjecture. So the Kazhdan-Lusztig conjecture involves something over here which is basically something of a completely algebraic nature. Namely certain representations, certain infinite dimensional representations of a complex semisimple Lie algebra, like a Verma module. And somehow we want to get across to here to Kazhdan-Lusztig polynomials, which are defined by some inductive algorithm. And how they do this is that they say that given a G module, you can produce something called a D module on the flag variety. And a D module you should think is something like an algebraic differential equation. So you have this differential equation, and now you can solve this differential equation to get a sheaf. In the same way that you take, for example, if you have a vector bundle with flat connection, then you can take the flat sections of this vector bundle and get a local system. This is what's going on from here to here. And these guys are what give you local intersection cohomology and take you to Kazhdan-Lusztig polynomials. So it's the most extraordinary kind of journey through 20th century mathematics. I should say that this connection was based on Deligne's proof of the Weil conjectures. So even this bridge is rather deep. Each of these bridges is extremely deep. So this bridge was established by Kashiwara. It's called the Riemann-Hilbert correspondence, and he received the Chern Medal this year at the ICM for this for many things, but part of his most significant results is this connection. And then Bayliss and Bernstein explained 10 years later that if you make this picture even more complicated, then it gives the Janssen conjectures. But I won't explain this. So there's this beautiful quote from Bernstein. He has these lectures on D modules that have never been published, but they're available. He says, "The amazing feature of the proof is that it does not try to solve the problem, but just keeps translating it in languages of different areas of mathematics, further and further away from the original problem, until it runs into Deligne's method of weight filtrations, which is capable of solving it. So have a seat. It's going to be a long journey." It's really an extraordinary... It's also amazing... So this conjecture was made in 1979, and then this proof came out a year later, but it's one of the most... I mean, it's by far the most difficult proof in representation theory. And so the fact that this came a year later after the conjecture is just extraordinary. Okay, so now we go back to much more elementary things. So I want to explain in some rough terms an elementary proof of this conjecture. So we come back to the flag variety, and I want to describe a simple algebraic description of a cohomology ring. So what we do is the following. We consider a polynomial ring in n variables, and this has a natural action of the symmetric group by permuting the variables. And the symmetric polynomials, E1, E2 up to En, form... So these generate the invariants under the symmetric group. And in fact, they give a polynomial subring inside here. And what we do is consider the ideal generated by these elementary symmetric functions and consider the quotient. So this is a rather explicit object in commutative algebra. This is a finite dimensional graded commutative ring. And what the Borel isomorphism tells us is, in fact, the cohomology of the flag variety is isomorphic to H. So this is a rather complicated space. So do I do the example of... No. So I'll just do the example of SL2. So for n equals 2, what is H? So this is a polynomial ring in two variables modulo the ideal generated by x1 plus x2 and x1, x2. And so this tells me that this relation tells me that x1 is minus x2. So this is isomorphic to x1 modulo x1 squared, and this is precisely the cohomology ring of P1. Okay, so it's a beautiful, simple algebraic description of this cohomology ring. Now, so this space here is something that depends on the existence of something like SLN, of a reductive algebraic group. But this description here only depends on basically having this graded ring with an action of a reflection group. Yeah? And that's where we're going now. So this is called shadows of Hodge theory. So I want to recall that we have Weyl groups. So Weyl groups are the skeletons of reductive groups. And these are examples of real reflection groups, which are examples of Coxeter groups. So if I take the symmetry group of the icosahedron, then I get a reflection group, and it's a reflection group of type H3, and this is not a Weyl group. This does not occur as the Weyl group of any complex semisimple Lie algebra. Okay? Whereas the symmetries of the triangle do, this is the Weyl group of SL3. And what Coxeter noticed is that real reflection groups have a beautiful presentation. And then he just considered groups emitting this presentation, whether or not they're finite, and he got Coxeter groups. And so, for example, if we take the symmetries of this picture here, we get a hyperbolic Coxeter group that's infinite, and it's an extremely beautiful group, but it's not the Weyl group of any kind of object in group theory. No? It's a very nice group, but it doesn't arise as a Weyl group in any reasonable sense. So, what we can do, before we took the symmetric group, we took a symmetric group acting on a polynomial ring, and we built out of this a finite dimensional graded ring. But what we can do is we can take any real reflection group acting on a real vector space, and we can imitate the same thing. So this would be similar to the example we just considered, whereas this example is something new. And what we consider the polynomial functions on our vector space, and we view it as graded with elements of the dual space in degree 2. So in the example of the symmetric group, this would just give me a polynomial ring with these guys in degree 2. And we do exactly the same thing as before. We take the W invariance of positive degree and form this quotient. Okay? So we're forming this finite dimensional graded ring. And just want to emphasize again that if W is a Weyl group, then this ring is the cohomology of the flag variety. So there is a space such that this is the cohomology ring of this space. But if I take this example, we don't know any space that has this as its cohomology ring. Any natural space that has this as its cohomology ring. Okay? So now this is a little technical, so I just consider the number of reflecting hyperplanes. So this is some analog, D is some analog of the complex dimension. And we have some invariant form. So what is this in geometry? So on a cohomology ring, I have the Poincaré pairing. So if I have two forms, I can form their wedge product and integrate them over X, and this gives me a pairing extremely important pairing on the cohomology ring, and what I'm doing is just imitating this. So it turns out to have a unique form that you can call the intersection form. So all of this is rather easy to see. So, and there also exists some open cone. So this is the toy model of our main theorem. So this is a finite dimensional graded algebra, this H. And so I have pieces of each degree. And now what I can consider is just multiplication by a general element of degree 2. So I get a map from here to here, from here to here, from here to here, and from here to here. Now the extraordinary thing is that if gamma lies in some well-defined open subset, something analogous to the Kähler cone, then what I get is repeated multiplication by gamma gives me an isomorphism from here up to here, from here up to here. Okay, so this is called hard Lefschetz theorem. And under my form, so my form gives me an isomorphism between this and the dual of this, and this and the dual of this. But now, once I've chosen one of these gammas, I also get an isomorphism from here to here and from here to here. So I have both an identification of this with this and this with the dual of this. And so I can put these together to get a form on this. So I get a form here and a form here and a form here. So another way of saying it is if I want to pair an element here with another element, I take my first element and I use gamma to take it up to here, and then I just pair these two elements. So I get some symmetric form on each of these vector spaces, and what the Hodge-Riemann relations tell me is what the signature of this form is. Okay? And I don't want to go into too much detail about what this is, but you can think that it's just a statement about the signature of a form. The interesting thing about this theorem is that if I start off with a Weil group, then I have this space called the flag variety, and I have this Borel isomorphism, so I know that these groups here are actually the cohomology groups of an algebraic variety, and therefore I can apply Hodge theory and deduce these two theorems. But if my W is, for example, the symmetries of an icosahedron, then I have no Hodge theory to tell me that this is true, but still it's true. Okay? So I just want to give you some examples of what these spaces look like. So these are Betti numbers of, so if I take the symmetry groups of symmetries of the icosahedron, then this is the Betti numbers of my space. So that in degree 0 it's one dimensional, in degree 2 it's three dimensional, in degree 4 it's five dimensional, etc. And if I take this is another example of a reflection group that is not a Weil group, the symmetries of the 120 cell inside R4, I get this vector space. So, I mean, the fact that a particular map from this 100 to this 100 is an isomorphism, factoring through all of these maps, is kind of remarkable. And then here's what it looks like for E8. Yeah, so it's enormous, rather beautiful ring. Yeah? So now we return to the Kazhdan-Lusztig conjecture. So this statement here is some toy model for the main theorem that would establish the Kazhdan-Lusztig conjecture, which is the following. So before, what I did was, I defined what Schubert varieties were, and I said that there's this simple algebraic method for describing the cohomology ring of the flag variety, this Borel isomorphism. What Zergel did is he explained how to give a combinatorial definition of the intersection cohomology of any Schubert variety. So he gave a combinatorial definition of certain H modules, HW, and so these are called Zergel modules, and what he showed is that the Kazhdan-Lusztig conjecture is equivalent to these modules having dimensions predicted by Kazhdan-Lusztig theory. And it's rather remarkable because these guys have some rather simple definition that lives purely in the world of commutative algebra, and yet the Kazhdan-Lusztig conjecture makes a rather bold prediction for the dimension. Okay, very precise. And somehow both sides of this are inductive, and so this is rather difficult to establish. And he used this decomposition theorem basically to show you that if you have very sophisticated tools in algebraic geometry, then these are isomorphic to certain cohomology groups of Schubert varieties. And what we do is we prove this equality by establishing the hard Lefschetz and Hodge-Riemann relations for each of these HW. So the example that I gave before of the co-invariant ring is one of these, but you have to establish it for W many of them. So there's some kind of remarkable resemblance to Maschke's theorem. So on every single one of these HW, there is a unique invariant form up to scalar. Completely unique. That's kind of uniqueness of geometric structure, analog of Schur's lemma. And also this invariant form, i.e. keeping track of this form, is our main tool in proving Zergel's conjecture. So this is analogous to Maschke's theorem in that you introduce extra structure in order to prove something. And Di Cataldo and Migliorini wrote some beautiful papers that provided enormous help. And also there's this whole world of diagrammatic algebra that I won't go into, but diagrammatic algebra allowed us to do kind of these big calculations that somehow make you sure that things are true, and so you know what to prove. So I just want to give one nice little bit in the proof. So imagine that I have a family of geometric structures. So on a real vector space, this is just a family of non-degenerate symmetric forms. Okay. Then because my forms are symmetric, I know that all of the eigenvalues are real. And so my signature is measuring how many eigenvalues are to the left of 0 and how many are to the right. And as my form moves, these eigenvalues move around in rather complicated ways. But if any of these eigenvalues wants to change from positive to a negative value, it has to cross 0. And so at that point, my geometric structure will not be non-degenerate. So as long as I know that all of my geometric structures are non-degenerate, the signature has to be constant. A very important basic fact, very useful. And this implies that if I have a family of Lefschetz operators, so these are these degree 2 operators going up, a big part of the proof is in changing these operators and moving them around. And the lemma, this basic lemma, implies that if one of these satisfies the Hodge-Riemann relations, this statement about signature, then in fact they all do. So when I introduced Kazhdan-Lusztig polynomials, I said that they're given by some recursive algorithm. And these only depend on a Coxeter group. And when Kazhdan-Lusztig computed an enormous number of these polynomials and saw that they always have positive coefficients. And if you believe the Janssen conjecture, then this is actually telling you, because these coefficients are measuring a multiplicity in a particular module, they have to be positive. But there's no reason why they should be positive for any Coxeter group. And actually what we do just goes through in general, and so we get that this positivity conjecture holds. And this I find a completely interesting mystery I call it mystery for the 21st century. So there's this extraordinary theory of the theory of non-rational polytopes. So if I have a rational polytope, I can associate a toric variety to it, and Hodge theory can tell me remarkable things about, for example, the cohomology of this toric variety. But if my polytope is non-rational, I don't have a toric variety, and yet these Hodge theoretic statements still hold. And this is used to establish statements in combinatorics about face numbers of polytopes. And there's this recent work of Apridizatu and Katz on matroids, which has the same flavor. They define, for any matroid, they define something that should be the cohomology ring. And if my matroid is realizable, it is a cohomology ring. But in general, most matroids are not realizable, and so I get something that looks like a cohomology ring but isn't. And why on earth, the structure given by Hard, Lefschetz and Hodge-Riemann is really, really strong and non-obvious, and why on earth is it showing up in these different situations? I think, it's very, very interesting. So just quickly, maybe you're wondering what happened to the Janssen conjecture. So Zergel and Kubel basically showed that the Janssen conjecture would be implied by some local Hard Lefschetz statement for these Zergel bimodules. Zergel bimodules are some, I won't explain, but there's something like Zergel modules defined in some commutative algebra framework. And then this local Hard Lefschetz theorem holds, and basically the same techniques apply. So invariant forms, deforming them, Hodge-Riemann relations are all important. This just happens to be insanely technical. And so now in the last 20 minutes or so, I want to talk about modular representations. So remember, I gave this example at the start of the lecture where if we take this representation of the symmetric group on 3 letters, in characteristic 0 it's semi-simple, and in characteristic P it is not semi-simple anymore. And so this is the world of modular representations in characteristic P, and there's just an enormous number of open questions in this field. Essentially any question you ask in modular representation theory, we don't know the answer, basically. It's just amazing. And so And there's also very, very interesting questions to number theory and algebraic geometry, which might also explain why these questions are so difficult. So, just briefly, I want to recall this example from the first lecture. So, we consider S3 acting via permutations of coordinates on a three-dimensional vector space. And we have these two invariant subspaces staring at us, namely all coordinates equal and the coordinates summing to 0. And if I take something inside here, it's of the form lambda, lambda, lambda. And then if I ask, is it in here? That's asking, is 3 lambda equal to 0? So that's the case if and only if 3 is 0 in my field. So if 3 is not 0, I get a nice direct sum decomposition. Otherwise, I get a composition series. And this is what we'll be studying, decomposition numbers. So I take some guy that's defined over the integers, I reduce it modulo p, and I ask which guys occur with which multiplicities. So what a very important thing in modular representation theory is to consider algebraic representations of reductive algebraic groups. So we take some algebraic group, like a reductive algebraic group like GLN, or I can read Windows.
One more hour.
So we consider homomorphism, so we consider representations in the category of algebraic groups. So if this is a finite group, we just consider all homomorphisms. If this is a Lie group, we consider continuous maps. Here we consider homomorphisms that are homomorphisms of algebraic groups. Okay. And why do we study reductive groups? In fact, the study of simple representations reduces to the case of reductive algebraic groups. So now we have this Lusztig conjecture. So when the Kazhdan-Lusztig conjecture was made, there's an obvious analog with this rational representations. Okay? And Lusztig made the kind of obvious conjecture that you would guess from the Kazhdan-Lusztig conjecture. And this approach of Zergel, these Zergel modules and things, is very, very useful for attacking this conjecture. Okay? But here we're modulo p, so signature no longer makes sense. So the reasons that Kazhdan-Lusztig conjecture were holding are kind of not available to us. We have no notion of signature. And now we have certain invariant forms, but now they're integral invariant forms, and we have to know, for example, their determinants. This is very hard. So there's a kind of extraordinary, so this is the Lusztig conjecture. I won't go, so this is some Verma module-like object. It's now a finite dimensional thing called a baby Verma module, and this is my simple module. And these are something like Kazhdan-Lusztig polynomials, so it's a complete analog to the Kazhdan-Lusztig conjecture. So it's the analog of the Kazhdan-Lusztig conjecture. The Weil group is replaced by the affine Weil group. This was this group that I displayed in the first lecture, where we add translations in the root lattice to the Weil group. And an enormous amount of work in the 1990s showed that this is true for large p depending on the root system. So up until phi big, we had no idea when it's true. We know for SL8, at some point, for large p, it starts being true, but nobody can tell you which p. And then phi big comes along and says, as long as p has more than 100 digits, we're fine. Okay? But one should say that here one hopes that it's true for p starting from 11. Okay? So there's a big gap between, we hope it's true for p bigger than 11, we can show that it's true as long as p has 100 digits. And what I showed in 2014, building on work with Schuhacher, is that it's false for primes growing exponentially in the rank. So, for example, it's false for p equals 470 million for SL100. Okay? Kind of crazy. So we expected that this is true for p bigger than 100, but actually it's false for this prime. And it's also false for all primes below this prime. Okay? So we need a new version of this statement. So this is true when our primes are very large, but we have no idea what's going on in the intermediate territory. And somehow there's a story of parity sheaves that I won't go into, but there's some kind of replacement of intersection cohomology or with mod p coefficients. And this leads to Kazhdan-Lusztig polynomials where I put a little p up on the left. And these vary depending on my p. And recently, after some enormous amount of work, we showed a new version of this character formula where the only difference is that these guys get a little p on the left. But somehow this big difference. And these guys are computable via diagrammatic algebra and computer. And so basically, so this formula takes us from kind of complete knowledge for something like SL. So before this formula we had complete knowledge for something like SL2, SL3 and SL4, and now we could probably get up to something like SL8 or something. So it's I mean, there's still many mysteries, but we are making progress. And this theory on this slide also has kind of direct relevance to the modular representation theory of what I believe is the most fundamental of all finite groups, namely the symmetric group. So I said before that if you ask a question in modular representation theory, almost certainly we don't know the answer. And that's the case here. We have no idea about the modular representations of the symmetric group. It's kind of shocking. I mean, we know some things, but almost any question you ask, for example, what is the dimension of the simple module? We don't know. So over the complex numbers, we understand irreducible representations rather well. So to any partition of n, so any way of writing n as a sum of decreasing positive integers, we can associate a Specht module, and this guy is defined by integral matrices and it's irreducible over the complex numbers. So this gives us a bijection between, which you may have seen. If simple representations of the symmetric group are in bijection with partitions of n. But now what we can do is we can take this guy, it's defined by integral matrices, we can reduce mod p. And this is this question that people have worked an enormous amount on. So take this guy, reduce it mod p, how does this guy decompose into simple modules? And it turns out to be extremely complicated. So it's only known for partitions with 1 or 2 rows. Okay, kind of shocking. So if my partition has 1 row, then this is the trivial representation, and so is this. So 1 row is completely trivial. And 2 rows is given by some very, very interesting fractal tree. So this is some picture of it. Okay? This is basically, I won't explain exactly what this picture is, but this is the rows of these. This picture is basically telling you how a simple representation decomposes when you reduce it mod p, and in this case p is 3. Okay? And you can imagine, so here we have these 3 branches, and then these 3 branches repeat, and then it repeats again, and so as you go off to infinity you get this beautiful fractal-like picture. And I just want to show you a video of this billiards conjecture, which predicts many new decomposition numbers for 3 rows. So this is still a conjecture, but so a large number of people have thought about this case of 3 rows, and there wasn't even a guess. And this technology with parity sheaves and Kazhdan-Lusztig polynomials and stuff leads us to a guess as to what's going on in many new cases. And I want to show you this video. So this is on YouTube, and it has 830 views. So I'm hoping to beat Gangnam Style, but I think I have a little while to go. So now I will try to show this video. So before I show you this video, so what we're doing is so it turns out that there's a 1 parameter family of questions for 3-row partitions. So we can, could you, is it possible to loop the video? Is it possible to loop the video? Or I can just play it again. Oh, okay. That's okay, yeah. Okay. That's what it looks like. Okay, so I just want to explain what this picture is showing. So what we're looking at here is that there's a one parameter family of modules indexed by this number that's shooting along here. And then what we're illustrating is how these modules are decomposing modulo p. So these are indicating the simple modules that are occurring inside this one parameter family of modules. So we have, and we think about this parameter as time, and then somehow when we plot this in time, you start getting this kind of remarkable billiard-like structure. And the reason that I find this so remarkable is that somehow it's difficult to imagine a more discrete problem than representations of symmetric groups in characteristic P. It's an incredibly discrete thing. But in the limit, it looks like it's approximating some kind of continuous billiards-like dynamic. So thank you very much.